Hello, it's Doug Littrell again. I'm making another video in my living room. This time I'm going to show what I think the lithium nucleus looks like and why. This is video 33. I haven't made a video in a few days. I don't know, it's been several days, I guess. Uh, this is July 16th, 2017. I've painted some hollow plastic balls. Some of them light blue and some of them kind of a dark purple. And these represent protons and neutrons. And this is how I think the lithium nucleus configures. I'll tip this. I've got some regular typing paper, 8.5 by 11, that I've sprayed some spray adhesive on, and so they would stick. Eventually, I'll hopefully have some Velcro balls so I can do this. But right now, I have to make do, and I'm going to tip this so you can see them. Those are stuck to the paper. Those light blue balls. The light blue balls in my system represent protons. The deep purple, I couldn't find a dark blue when I looked for some spray paint. So now when I draw these on my website or Facebook page, or in the new periodic table I'm working on, I sometimes use this deep purple because when you're looking at the configurations, the light blue balls, the lightest blue balls are the protons that are nearest to the viewer. The darker they get, the farther away the protons are. Now, in my system, it looks like there is roughly 5 to 6 times more protons than neutrons in the universe. There's good reason for that. My system explains why. But anyway, what the nuclei are doing, or what the protons and neutrons are doing in a nucleus, is they're trying to keep the neutrons separated because they have higher charge. They have higher charged photons on their surfaces, trying to neutralize the low charge. All of the low charged are especially uncharged. Most of the I don't know about black holes. They probably contain lots and lots of uncharged photons, and that's probably the origin of black holes. But as far as the particles out there, most of the black uncharged photons in the universe are inside of neutrons, and they're the black in my system. If you look at my new periodic table. By the way, when I'm talking about periodic table, a new periodic table, I couldn't have done it without the one we have, the great work, the one we have now, all the fantastic work that's been done, so I could come along and tweak things and say, oh, okay, there's no negative charge, so how would it work? The only reason that one needs to be replaced eventually is because if negative charge doesn't exist, then your basis for your atomic weights, that's off, and how many protons and neutrons are in a nucleus, that's off. What they do have correct, and what I use, is the mass. The mass of protons and neutrons are essentially the same. Now, if you look at my new sheet on, for all the atoms and the configurations that I'm drawing right now, I'm up through argon, and I have my explanation of my system at the top, and I just posted that yesterday on Facebook. But if you look at that, you'll see that the positron I drew yesterday and posted, it has a mass of 59. And what I've shown in 2014 is that a positron had a mass of 67. But the thing you need to know about positrons is they can vary in mass. That would be the least probably the very least massive positron you could have would be a mass of 59, compared to a beta 43 that has a mass of 43, and then a beta 27 has a mass of 27. Now those beta particles are have less room to vary in mass. They could a little bit, but they're very symmetrical, and you need symmetry in the universe, or something has an edge on it that can get bombarded in the environment, and it would not last as well as something that is more symmetrical. And or and the idea is to be spherical is of course the best. And but these things aren't always perfect spheres, of course. Let me try to help this stay up here with this, holding this a little bit. Anyway, so if you have positrons, if they can vary in mass more so than the beta electrons, now you have the mass of a proton and protons and neutrons can vary, because now they wouldn't. Some of those that they contain are going to be pretty uniform. There's going to be a favored pattern of the positrons that are in protons and neutrons. But both of them, in a neutron, there is the highest charged photon in the center of its center unit, and that means it needs more uncharged particles, or low charge, but in this case uncharged, because they're even more highly attracted to the highest charged photon than, say, the next step up in charge from the uncharged, which would be the dark blue in my system. But the blacks would be so massively attracted by charge contrast, they would attach and cover it, and they would beat the dark blues to it. So inside of a neutron, in its center unit, you have a white, and then it's covered over by blacks, and then it takes more mid positives to cover that over and try to neutralize it, which was what gives neutrons their somewhat more, a little bit more mass than the protons have, is that high charge center photon trying to get it neutralized. And then you need more of the uncharged, and then because there's more of the uncharged, you need more of the mid positives. And then the higher mid positives do a better job. You don't need as many of those if you have more of the higher charged mid positives. But in the environment, you don't always have everything available in equal proportions. So that's why they make different, and that's why different nuclei form, different elements form, because they're going to just form naturally by attraction, and there's and whatever proportions are in a certain location, that's what it's going to make. And that's when it comes to making protons and neutrons. Also, when it comes to making nuclei of atoms, the elements. So you don't need any heat for this to happen, and this is just going to happen by attraction and repel. Everything is going to just make it. It's just going to make these atoms, and it's going to make these protons and neutrons. Now, inside of a neutron, you've got the pink, the second highest charge in my system. When it's made, it's experienced less compression. The white experiences the most. It comes out and retains more of its cube shape. They reflect back to being spheres again. That's why they burst out into space in two opposite directions, but from a collection. But the highest charge retains more of its cubic shape under that compression. It does flex back to being more spherical. So does the pink inside the center unit of the proton. But that's how they get their impetus to push out into space from a giant collection with massive gravity that we can't even hardly imagine. It's so great, the gravity. But anyway, this inside of a proton, you've got a center unit. It's not as massive because it doesn't take as many of the uncharged and very low charged photons to cover its pink, and then it takes less disruptive, or rather lesser charged mid positives to cover it over. So they generally have less mass, but the the masses can vary because the positron can vary. Just like in my latest sheet at the top when I drew the 59 mass positron, that one had utilized the repel of one of the highest charge photons that's flowing in the environment. Usually they're on a radio particle, the R3 in my system, and they appear in other places as you see in my system in my latest drawing of these at the top of my new periodic table. But the positrons, that positron that I drew would be the least massive that I can imagine, and it would have 8. Let's see, is it 8? Yeah, I believe it's 8 yellow-orange photons basically on its surface or near its surface, and that helps it not need as much mass to neutralize what it's trying to neutralize, because there's more repel in those. And so that one has a mass of 59. Now, if those yellow-orange photons weren't available in the environment, then it would be adding more of the yellow-greens and yellows to do the same job, and then it would need more mass. So protons and neutrons are generally the same mass, though the neutrons have a little bit more mass because its center unit is higher charged. And it takes more on the surfaces of the positrons. You would also have some more mid-positives like yellow-orange or yellows attached on the surface of a nucleus. Now, because the center unit in both the proton and neutron is a little larger than a positron, you'd have 14 positrons in each that cover, generally speaking. There's probably another way you could make these in nature, but generally speaking, there would be 15. I'll go ahead and set that there. You would have, you'd have 3 stacked, let's say, and then like in R3, and then you could put 2 more here, and then you'd have a total of 6. You'd have, 2 of them in the, okay, you've got X, Y, Z, 3-dimensional. Okay, let's say that's X is up, and Y is this direction, and then Z is this direction. So you'd have 6 with the center. Oh, excuse me. The center would be, you'd have 2, 4, 6. The center, that's 7. Now, on that, you could put, if we're dealing with protons and neutrons, if it has a center unit and it's more mass, it's got greater volume and it's more massive, both. Now, instead of it making such a nice sphere, but here's how you make a sphere. Let's just imagine now that you've got the 7 unit like a radio particle, and you put 2 on one side, kind of in the valley, and 2 on the other side in the valley at the top. Now you go down lower and you put 2 there in the front and 2 in the back. Now you've added 8 to 7. You've got 15. So that's why you come up with the number 15 for those. And 15 is always appearing in my system because that makes a sphere. Now you have these valleys still left, and there's still more attraction. That's why you have electrons and radio particles that hover around in some orbit when there's a few enough of them. They hover around the nucleus because there's always more leftover traction, even with these protons and neutrons. So you got these valleys, and electrons and radio particles and individual photons particularly electrons, beta electrons particularly, would naturally come in and firm up those gaps, those valleys between them. And that's why you have beta radioactivity as well, because they're in those neutrons and protons. They're filling up those spaces, trying to make them spherical, so they work out and become a stronger particle that stands up to the collisions in the environment. But you would have these different things filling, you would have greater values because the center particle that these 14 positrons are encasing, uh, the center units of protons and neutrons is a little bit larger than the positrons. So that makes for greater values, and that's why you have these electrons in those valleys. And then you have other stuff too, probably some radio particles. You have individual photons. And this stuff is all trying to neutralize, more than anything, the uncharged particles in the neutron's center unit, as well as the low charged particles and a few uncharged in the positrons themselves, as I've drawn them in my latest periodic table. Now, as far as the way that lithium is configured, the way I've got it drawn is the protons with their milder surface particles, they can attach to one another, there's no problem. But it's just like an electron attaching in the valley, there's no problem. You've got mid-positive up against mid-positive, but it's not enough to create a problem. And it works fine. That's why you have electrons out and radio units out from there, because there's still more attraction. Those can't come close enough to attach. But anyway, in lithium, what's going on with all the nuclei I draw is that the protons, which are milder charged, are helping keep the neutrons apart. The neutrons, what they do is their interiors and exteriors are more contrasting in charge. You have a lower charge and the uncharged ones in the center unit, and then you have all of those are inside, and these have spaces between them that attraction and repel relationships all radiate through. They're not, when they're covered, that reduces it, but it doesn't go away. And so neutron to neutron, the interior particles are highly attracted to the exterior particles on both. The interior of this is attracted to the exterior of this, and vice versa. Now, when they come together more strongly than a couple of protons. Protons have a hard time making anything, you can't hardly make anything with just two protons. You need the attraction of neutrons present for a nucleus to work, because that it's in the collection that it becomes a nucleus, and the neutrons are what's holding it together. They just can't be together because they're too attractive, mutually attractive. And so when the interior of this is attracted to the exterior of that, and vice versa, they come in together. But now their surface repel particles are higher charged, and there's more of them, and so they repel. And then they're attracted again. And that's what creates most of the radioactivity that we observe. Now, another thing that can happen as far as radioactivity is concerned is whenever, not only clapping of neutrons causes that, and then some of those particles in the valleys, they experience too much repel and get pinched and it flies off. But they would want to restock that if they could get the same thing to come back. But anyway, this is radioactivity. But as far as protons being involved in radioactivity, that happens as well, because in some situations the valley isn't a neat valley on a nucleus, and there's a proton that was present when the nucleus formed, and it's attracted enough to stay, but it's in a precarious valley that maybe has further, it's not just neatly held in one spot, it can move back and forth, and that can create radioactivity as well. So protons are involved in some radioactivity also. But as far as a helium nucleus, what I want to say about, or not helium, but lithium, this is the way I've drawn it. You've got, in lithium-7, you have 5 protons keeping 2 neutrons separated. I wanted to show that it works. And so another thing I want to mention is when you bombard, say, lithium and, say, a cyclotron with protons, say, and you break it apart, that's how they make, isotopes for hospitals to do PET scans, as they come up with, they bombard stuff, and then that becomes a positron emitter, like say carbon 11 or nitrogen I forget now which one of nitrogen, but there's one of nitrogen, I believe, another one. There's a fluorine that's used for PET scans, isotope. But once you knock some of those off in say a cyclotron, now you've got some damaged, unstable neutrons and protons, probably mostly protons, and they're subject to knocking off more positrons. So that's how you get those for PET scans. And then of course, well, we don't want to go into all that, but as far as this nucleus is considered, I once was about to change how I would configure the nucleus, the lithium-7 nucleus, but I've abandoned that, and it's on my website. The reason why, because what happens when you bombard these, and they say you're not going to bombard them enough to break their positrons apart, but you bombard them enough so that the nuclei come apart. Okay, and so when you do that to lithium, it's been done. It's been noted that there's a lot of alpha particles coming out. And what an alpha particle is, it's two protons and two neutrons attached. And so let's take one of these. They're stuck. Okay. And you would have something on the order of this. Well, there's not really any other choice. That's an alpha particle. That's a helium-4 nucleus. Okay, a helium-3 nucleus, take away one of these protons, and you got a helium-3 nucleus. But anyway, when these come off, they don't come off attached. Probably most of the time they don't come off attached. But if you've got, say, two protons coming off and one neutron, and they're going to attach while they're moving through the air, okay? And then by the time they get someplace that they're going to be checked to see what that is, say some screen that can detect what it is, then they're going to be together because they're attracted. When they're flying along after they've been ejected from a nucleus, they're going to attach. They don't come off attached most of the time, probably. And the same thing now, if two neutrons come off and two protons, they don't have, maybe they're attached like that, but they form an alpha particle or helium nucleus as they're flying through the air in destination to wherever they're going. They make that while they don't have to come off as a perfect helium-4 nucleus or helium-3 nucleus. So, and so that really affected how realizing that affected how I configure lithium, because what you would have to be noted is when they bombard lithium is, if this configuration is correct, is they would need to check and see if there are, so you would have two and two, let's say, would be the alpha particle, generally speaking. So you would have three protons as well. Now, are they sensing that a lot of protons are coming out of that bombardment situation as well? But I really do believe that the lithium nucleus is configured just like this, and then you have the other neutron on the other side. So